So good morning everyone and welcome to today's lecture. This is work by energy lecture number 24. Well, we have already done work by energy as such. The better name would be, let me change this. This is work by energy lecture number 24. But what we are going to deal in this lecture is circular dynamics or circular motion. Circular dynamics or circular motion. Now I am aware that you have already covered the circular motion, but as I said, whatever is required, take it as a revision as well. We would be covering in this chapter because most of the circular motion that you encounter would be coming in this particular chapter. Now on same lines, what we had done in the previous class, let us have a quick recap of what we had done in the previous class. So if you recollect, in the previous class, we were discussing the basic concepts of circular motion. What are the basic concepts of circular motion? And if you could recollect, we had discussed what is circular motion. If a particle is moving in a circular path, what is a circular path or what is a circle? A circle is the locus of all points. If a particle moves in such a way that its distance from a fixed point remains constant, that fixed point is known as the center of the circle. Now, we had also seen that that point may not be fixed. It can also be moving. In case of a cycle, if you think of a point on the rim of the wheel that is moving in a circular path, but the center of that circular path is constantly changing. So we have read about the definition of circular motion. Yes, I hope you all remember that because it has been, I think, 7 days since our last class because you had a long vacation. So can I have some raise hand that you remember what is circular motion? Just to have a quick recap, okay? Remember this. Only Abhiram seems to be interested. What about the others in the class? Are we there? Akshaya, Tarun, are we there in the class? Okay, great. So we had discussed what was circular motion. Then we had also discussed the different terms that are going to come in the circular motion. The first term is angular position. It is same as the position vector. But remember, this angular position is given in terms of an angle that this particle makes with the x-axis, this angle. And since this is an angle, this is not a vector, this is treated just as a scalar quantity. Angular position is same as position vector in your translatory motion. I think we also discussed there are three types of motion: pure rotation, pure translation, and a mixed motion. We call it plane motion also. Here we are going to study pure rotation. It is not rotation right now, it is only circular motion. And I also told you that whatever term we have studied in that translational motion, the same term would come here. Angular position is same as position vector. The second term is angular displacement, which is same as your displacement vector. So whenever you change the position of a particle, it gets displaced. Final position minus initial position. Here it is final angular position minus initial angular position, which is change in angular position. Delta standing for change, theta standing for angle or angular position. Delta theta is the angular displacement. We also seen that angular displacement for small quantities is vector, but for large angular displacement it is a scalar quantity. I hope you all remember this. raise hands will give me more confidence that yes, sir, we remember this angular displacement and angular position. Great. That takes us to the next point of this. We are doing a big recap because of the time, because of the difference in the classes. Angular velocity, this is same as your velocity. It is denoted by the letter omega. Then there are two types of angular velocity. One is average angular velocity, is total angular displacement divided by total time, delta theta divided by delta t. And this quantity is a scalar quantity because delta theta, which is change in angular position or angular displacement, we are talking about large angular displacement here. This is a scalar, and hence angular velocity is a average angular velocity, I must correct myself. Average angular velocity is a scalar quantity, theta 2 minus theta 1, which is angular displacement or change in angular position divided by total time. Then we have something known as the instantaneous angular velocity, which is same as your instantaneous velocity. Now, this gentleman is omega vector because it is a vector quantity d theta vector by dt. Remember, this vector is known as an axial vector. What do I mean by an axial vector? When you have an axial vector, its direction is given in terms of an axis on which that body is rotating or turning or performing circular motion. For example, and the direction is given by the right hand screw rule or right hand thumb rule. What does the right hand screw rule or right hand thumb rule says? For example, if this is positive x-axis, this is positive x-axis, I hold the positive x-axis in my right hand. This is how I hold positive x-axis in my right hand, my thumb pointing towards positive x. Then the direction in which your fingers turn, the direction in which your finger turn gives you the direction of rotation. In this case, if this is positive x-axis, if something rotates like this, it is rotating on positive x-axis. If something is rotating on negative x, it will rotate like this. If something rotates on positive y-axis, it will rotate like this, axial vector. If something rotates on negative y-axis, it rotates like this. If this is your positive z-axis coming towards you, something rotates on this axis, it rotates like this. It rotates like this. If this is your negative z-axis, it rotates like this. This is how axial vectors are defined. We would be requiring these axial vectors in the chapter of rotation. You might have heard about these axial vectors in the direction of in the chapter of rotation. Angular momentum is an axial vector, torque is an axial vector. All these vectors, the direction is given in terms of the axis of rotation. Instantaneous angular velocity is an axial vector. This is a vector, an axial vector. We had done this. Then we had done something very enterprising here, that we had talked about if a body makes n rev rotations in t seconds, the average angular velocity is given by this and the time period is given by this. Now, I did not elaborate much on this. I am going to do that now. What do you mean by this? I will elaborate this now, and let me discuss it in different points. So let me just bring my writing board on your screens, and your writing board should be visible to you now. Now we have talked about angular velocity. Now what happens What happens if your angular velocity is constant? If angular velocity is constant, then what happens? If angular velocity is constant, then your instantaneous angular velocity omega, which is omega vector, taken the modulus of that. Or instead of making it so complicated, let me just write it in terms of words. If your angular velocity is constant, then when I say constant, I mean it remains same or it does not change with time. When your angular velocity is constant, then your average angular velocity, will be equal to your instantaneous angular velocity. Now, average angular velocity is a scalar quantity and instantaneous angular velocity is a vector quantity. So I'm not talking about the directions here. I am talking about the magnitudes here. Your average angular velocity and your instantaneous angular velocity will be same. This is same as saying, please listen to me very carefully. If your speed is constant, your average speed and instantaneous speed will be same. If your velocity is constant, your average velocity and instantaneous velocity will be same. If your acceleration is constant, your average acceleration and instantaneous acceleration would be same. If your power is constant, your average power and instantaneous power would be same. Do we understand this? Can I have some raised hand that we understand this? If your angular velocity or speed or power or acceleration, the next term will be angular acceleration. If all these things are constant, then your instantaneous value and average value would be same. Can I have some raised hand that we understand this? Everyone? Okay, so this point is clear. It is valid for all the terms that we have done so far. Now, if this angular velocity is constant, and again I will mark it as second point, if angular velocity is constant, angular velocity, let me just call it as omega, is constant, then the motion is known as, the motion that it is happening, that motion is happening in a circular path, that motion is known as uniform circular motion. I hope you have heard this term, uniform circular motion. In short, it is known as UCM. Do we understand this? If your angular velocity is constant, then your motion will be known as uniform circular motion. It is same as if your velocity is constant, your motion is known as uniform motion. If your angular velocity is constant, then your motion is known as uniform circular motion. In short, you can call it UCM. Do we all understand this? Can I have some raised hand that we understand this? Uniform circular motion. Your angular velocity is constant, the motion becomes uniform circular motion. Now, when the motion becomes uniform circular motion, you can write the heading as UCM. UCM. What do you mean by UCM? So what is the first point about UCM? Number one, angular velocity omega is constant. Angular velocity omega is constant. Number two, I can write omega velocity, right? Okay, I just not want to make it complicated for you guys. So what I'll do is We just take this down. So your average angular velocity would be equal to your instantaneous angular velocity. And here I am only talking about the magnitudes, because average angular velocity is not a vector. So two things are pretty clear here, that your omega is constant, angular velocity is constant, and your average values and instantaneous values would remain same. Now, if this happens, what will happen? If your omega is constant, it will always take same time to complete one revolution. It will always take same time to complete one revolution. Now, when this revolution comes, I hope you understand one revolution is one full circle. Then you can also think about motion that you see in your day-to-day life, which are UCM. Can you give me an example of a motion in your daily life which is a uniform circular motion that you see every day? Omega is constant. Omega is constant. Oops, wrong color. Omega is constant. Average angular velocity is equal to instantaneous angular velocity. Third point I can write, it will complete one revolution in a fixed time. Always it will complete one revolution in a fixed time. Now can you tell me, now can you give me an example of uniform circular motion from your day-to-day life that you see every day? Anyone? It's a simple question. Your rotation chapter is finished, so I'm sure you must know about UCM. This is 7th, 8th, 9th, 10th standard physics. Example of a uniform circular motion. It will complete one revolution in a fixed time. Think about phenomena that you see where one revolution always takes a fixed time to complete. Anyone? No one? Clock hand. Yes, Abhiram, that is correct. Look at you have a clock on your walls in your home. And I hope it is not a digital clock which just shows you the time. I hope it is a clock which has a hour hand, which has a minute hand, and which has a second hand. If you look at the motion of the second hand, seconds wala hand, or minute wala hand, or hour wala hand, they are performing uniform circular motion. They're always completing one revolution in a fixed time. In how much time? The second hand completes one revolution. The second hand completes one revolution in 1 minute. The minute hand completes one revolution in 1 hour. The hour hand completes one revolution in 12 hours. The earth rotates on its axis 24 hours. The earth revolves around the sun 365, and some days fixed. It changes by a very small amount, but for our practical purpose we can take it as fixed. So whenever you have a uniform circular motion, one revolution would be completed in a fixed time. That time, or for that matter, time taken to complete one revolution, time taken to complete one revolution time taken to complete one revolution is known as the time period. Time period of UCM. This term is basically used in UCM only because this time period is fixed. It is denoted by capital T. Time period of uniform circular motion. It is a time taken to complete one revolution. You can also define time period for non-uniform circular motion. But in that case, the time will be continuously changing. So time period does not make much sense. We don't normally call it as time period. We just call it how much time it will take to complete one circle, because that time is not fixed. Therefore, this time period term basically comes in uniform circular motion. Now this will be coming very often, very regularly. So you must remember what is time period. Now once you have this time period capital T, you also have one more term which is known as number of revolutions in 1 second. And that number of revolutions that a body takes in 1 second, how many chakkar, how many revolutions it is taking in 1 second, is known as the frequency. Number of revolutions that you must remember, number of revolutions per second is known as the frequency of uniform circular motion, denoted by normally small f. I hope you understand this. Time taken to complete one revolution is time period. Number of revolutions in 1 second is frequency. The SI unit of frequency is hertz. The SI unit is hertz, and the SI unit of time period is definitely seconds. Now this hertz, gentlemen, if I talk about this, is 1 by second. This hertz is 1 by second. So now you can understand the relation between F and T. Now you can understand the relation between F and T. What would be the relation between F and T? It's very simple. It is 678 standard physics. Frequency is 1 by T. Do we understand this? Can I have some raise hand that we understand this? Frequency is 1 by T. Number of revolutions in 1 second. Frequency F is equal to 1 by T. T is a time period. Time taken to complete one chakkar or one revolution. Frequency is 1 by T. I'll give you a minute. Note this down. Then I'll proceed further. Well, I hope you have noted this down. Frequency is 1 by T. Now I will go ahead and give you more relation. Now this angular velocity omega, which is fixed. Now omega is 2 pi multiplied by T. 2 pi multiplied by t. So I can also write it as, oh, sorry, 2 pi divided by t. I've written it wrongly. Just correct it. 2 pi divided by t, or I can also write it 2 pi into f. Now, this is the complete analysis of your uniform circular motion. These two formulae or one formula, or whatever you call it, will give you a complete analysis of uniform circular motion. Here you must understand that your T stands for your time period, your F stands for your frequency, and your omega stands for angular velocity. Now this omega, which is angular velocity, has a very interesting name as well. We might not be using, we will not be using this name here in this chapter, but in your 12th standard, in a chapter known as alternating current AC, we would be using. In fact, in your chapter on waves, we would not be using angular velocity. In fact, in your chapter in SHM, also we will not probably be using angular velocity. We will be using angular velocity, but we will also be using one more term for angular velocity. This other term for angular velocity is known as angular frequency. So just understand and remember, this angular velocity and angular frequency actually means the same thing. Now we all know angular velocity is denoted by omega, so that is understood. Why is omega also known as angular frequency? Why is omega also known as angular frequency? The answer is right there in front of your eyes. See, this F is frequency. This F is frequency. You all agree on that? This 2 pi is an angle. This is the angle that it rotates in one circle. 2 pi, 360 degrees, is the angle that the particle rotates, moves in one circle. So 2 pi is an angle, is definitely an angle. Angle multiplied by frequency, angle frequency, it becomes angular frequency. So omega can also be called as angular frequency. And we will be calling angular frequency as omega. Omega as angular frequency is omega. Omega in uniform circular motion is known as angular velocity. Do we understand this? Can I have some raise hand that we understand this, sir? Okay. We are noting down some important points about uniform circular motion. F is equal to 1 by t. We all know this. Omega is 2 pi by t, and that is equal to 2 pi into f. There is one more small thing that you must remember, which might be coming in your questions, and I don't want you to be getting confused. There's one more thing that might trouble you sometimes. Sometimes it is given as, sometimes it is given as the body performs n rotations per second. If a body performs or completes n rotations per second, then you can have one more formula for omega. And what is that formula for omega? Can anyone tell me? No, sometimes it is given that body performs n rotations per second. So basically, if it is given in this way, remember, don't get confused. Don't get confused. Don't get confused. Don't get confused. This n rotations per second, this n becomes your frequency. Do we understand this? Sometimes it is given in this way. So you must not confuse it with anything else. This n is simply your frequency. So your n simply becomes equal to f. Please remember this. Don't get confused. Small things make a big difference in your life. If your body performs n rotations per second, your n becomes equal to f. Then your omega can be written as 2 pi n. Do we understand this? Can I have some raised hand that we understand this? Just written in a different way. You should not get confused with this terminology. One more way in which this can be written is this. And this is what we need to understand. Now I'm just going to change the, if a body performs, I hope you can see me. If a body performs n rotations in t seconds, then can you tell me what is the relation? I'll give you a minute to think. If a body performs n rotations in t seconds, what can you say about the relation? It is very simple. I will not take much time. Your frequency f will become n by t. Do we understand this? Yes or no? Number of rotations in 1 second. It is taking n rotations in t seconds. So how much rotation it is taking in 1 second? It is simple, n by t. Frequency becomes n by t, which implies your omega becomes 2 pi n by t. 2 pi n by t. Your time period becomes t by n, which is nothing but equal to 1 by f. Please remember these small points. These small points are the questions that are going to come in your exam, and you should not miss them at any cost. That is the prime important factor. I hope you are noting everything down. There can be a different variation of the same. If a body performs, now I'm writing capital N rotations or revolutions in 1 minute. 1 minute. 1 minute. You know what happens? Can you now tell me? It is very simple. Your frequency f becomes n by 60. 1 minute has 60 seconds. And the rest of the thing simply becomes omega becomes 2 pi capital N by 60, and your time period becomes 60 by capital N. Small things make a big difference in your life. I'll give you a minute to write all this down. If you have any doubt, please come up. I hope you all have noted this down. Can I have some raised hand that we have noted this down, sir? Okay. Now, the next point is in blue, if omega is not constant. If omega is not constant, then what happens? If omega is not constant, then the motion becomes non-uniform circular motion. Non-uniform circular motion. Now, omega is not constant. That simply means that this omega is going to change. This omega will change. This omega will change. That brings us to the next term. What changes omega? To understand this term, we go back in past and we have the ability right now, as Doraemon has. He has a time machine. He can go back in time. We also probably have a time machine and we can go back to the first chapter and see. We had velocity. When velocity was constant, it was uniform motion. Velocity does not change. It does not change in magnitude. It does not change in direction. But then we had velocity changing. Either it was changing in magnitude, kam zyada, more, less, or it was changing in direction. Sometimes going like this, sometimes going like this, sometimes going like this, or it was changing both in magnitude and direction. What was changing that velocity? What causes a change in velocity? What do we say when velocity of a body changes? What is the term that we use when velocity of the body changes? We say that the body is what? Body is not moving with uniform velocity. But what is the other term for saying that when the velocity of the body changes, what do we say? The body is what? Fill in the blanks. No one knows? When the velocity of the body changes, what do we call? We say that the body is accelerated. Acceleration, change of velocity. Whenever velocity changes, we say that the body is accelerated. Similarly, when the angular velocity of the body changes, we'll again call it accelerated. But now, this acceleration will not be called as simply acceleration, because the velocity is also not known as simple velocity. Velocity was known as angular velocity. Displacement was known as angular displacement, and hence acceleration will be known as angular acceleration. And that is the next heading. Please write angular acceleration. Angular acceleration means that the angular velocity of the body is changing. Do I make myself clear? When the angular velocity of the body changes, we call it the body is accelerated, and we call that acceleration as angular acceleration. This angular acceleration is denoted by the letter alpha. There it was denoted by the letter A. Here it is denoted by the letter alpha, which is a Greek alphabet, which is coming to your screen right now. It is on your screens. Angular acceleration denoted by the letter alpha. It is a vector quantity, so you can write a vector sign on top of it. Angular acceleration is a vector. Again, there will be two types of angular acceleration. No point of telling you what those two types would be. The first would be known as average angular acceleration, alpha, with a vector sign. It is a vector put in a dabba. This dabba means the average or the mean value. That will be final angular velocity omega 2 minus initial angular velocity omega 1. Remember, these two are vectors divided by the total time, or I can write change in angular velocity divided by total time. It is same as writing acceleration alpha, no, acceleration A, average acceleration A is v2 minus v1, or v minus u divided by t, or I can write it as delta v vector divided by delta t. Do we all understand this? Can I have some reason that we understand this, sir? Again, this is a vector and this is an axial vector. That means the direction is given in terms of the rotation axis. I'll give you a minute to note down what is average angular acceleration. Average angular acceleration. Now, if you have average angular acceleration, you also have instantaneous angular acceleration. Average angular acceleration is alpha vector in a dabba. Instantaneous angular acceleration. When I say angular acceleration, I mean instantaneous angular acceleration. Instantaneous angular acceleration is alpha vector. This will be d omega vector by dt. We all know this. Now, this omega vector is d theta by dt. So alpha vector becomes d square theta by dt square. If I write it like this, you can also write it as omega into d omega by d theta. Remember, all these are vectors. All these are vectors, but when we solve questions in uniform circular motion or circular motion, we will, instead of writing it as vectors, we will be taking signs instead of writing vectors. So remember our sign convention here. Now, there is a small thing that you must understand, that things can rotate on any axis. It can rotate on this axis, 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 it can rotate on infinite number of axes. That motion is going to be very complicated. If it is rotating on this axis, also accelerating on this axis, torque is along this axis, angular momentum is along some other axis, becomes a very difficult problem which is out of the course. What will be in course is bodies are going to rotate or move only along one axis. When I say only along one axis, whether it will be x-axis, or it will be y-axis, or it will be z-axis. Now, but on x-axis, they can rotate in two ways. It can rotate on positive x, or it can rotate on negative x, like this. If the body is rotating on y-axis, it will rotate like this, positive y, or it will rotate like this, negative y. More often or not, what is going to happen is when you do problems in UCM, the body will be moving in circles like this on your sheet. The bodies will be moving in circles on your sheet, more often or not. Now, when a body is moving in circles on your sheet, it can only move in two directions. It can only move in two directions. One is like this, the blue direction. The other one is like this, the red direction, the blue direction, or the red direction. This blue direction is known as anti-clockwise. Oops, I've used the wrong color. Okay. This blue direction is known as anti-clockwise, and this anti-clockwise, if I talk about signs, this anti-clockwise would be positive. Why would this anti-clockwise be positive? Because this anti-clockwise is along positive z-axis. Something rotates on positive z-axis. Positive z-axis will be coming out of your board. So if it is rotating anti-clockwise, it is rotating on positive z-axis, and we will call that as positive. If I call that as positive, anything rotating on negative z-axis, which is clockwise, that becomes my negative. It is same as if something is moving along positive x, we call it positive instead of calling it as a vector. This positive or negative tells us the direction. If it is moving along negative x, we call it negative instead of minus x vector. If it is using along positive y, we call it plus. Negative y, we call it minus. Positive z, we call it plus. Negative z, we call it minus. And hence, this is the sign convention that we are going to use in circular motion. Anything moving anti-clockwise is positive. Anything moving clockwise is negative. Do we understand this? Can I have some raise hand that we understand this, sir? No problems with this one. We are ready to go. Okay, you all understand this? I hope you have noted this down. I will give you a minute to notice down. I hope you have noted this down. Then there are some simple points that you can note down for angular acceleration. 2 points. Both average and instantaneous acceleration are actual vectors. The dimension is 1 by t squared, t raised to the power minus 2, because it is omega divided by t. Omega is 1 by t, so it is 1 by t squared. Unit is radians per second square. Omega is radian per second, so angular acceleration becomes radians per second squared. If alpha is 0, there is no angular acceleration, and the motion becomes uniform. Instead of calling it uniform, I'll call it uniform circular motion. Do we understand this? UCM. If alpha is 0, motion becomes uniform circular motion. Do we all understand this? Can I have some raise hand that we understand this, sir? So alpha is 0, the motion becomes uniform circular motion. What we have done in today's class, we have seen uniform circular motion, and we have seen what is angular acceleration. What I would request you as homework in the next class, I'm sure that you have done it before. These are the equations of motion in uniform circular motion. Equation number 1, equation number 2, equation number 3, and equation number 4. I'm sure we have done these equations before, not in terms of omega, but definitely in terms of VU. V is equal to U plus AT, delta R is equal to UT plus half AT square, V square is equal to U square plus 2 times A into delta R. We have done these equations before. I would request you to go through these equations once more, because we would be discussing these equations in detail in the next class to complete our journey for UCM circular motion. Don't worry, we will be covering each and every aspect of circular motion that is required. Once we are done with the next class, we would be moving on to circular dynamics and see what is circular dynamics. So I leave this class today at this point in time with this small homework that you will go through all these equations once again, which are very simple, not complicated. We have already done it. In the next class, we would be discussing these equations again. If you have any doubts, you can come up to me at any point in time. I'm always there. Stay at home and stay safe. Don't venture out. This is not a time to venture out. And I guess you all are also eligible to get vaccinated. I would request all of you to get vaccinated ASAP, as soon as possible. If you are in that age range, 15 to 18, I think you should be in that range. Please get vaccinated. Stay safe, stay at home. I also got vaccinated. I also got my precaution dose 2 days back. So that's the only way we can win this battle against the virus. It will keep on coming and going. It will be a part of our lives. We must understand this. Just like common flu or cough, everyone has it. We'll have to be careful. Stay safe, stay at home, get vaccinated. Follow social distancing if you have to go out ever. Don't go out. Stay at home. I'll see you in the next class with the small task that I've given to you. I hope you can do this class. This is a wrap from my end. I hope to see you in the next class. Take care. Have a good day.